All right, morning everyone, still morning, yes. This is PHP Under the Hood. My name is Davey Shafik, as you probably figured out from the schedule. I am a community engineer at Engine Yard. What that means is that this is pretty much my job, which is freaking awesome. I'm the author of the PHP 5 certification study guide, which I'm currently in the process of revising up to PHP 5.6. Should be out by ZenCon this year, which is October. Also PHP Master and PHP Anthology. This is actually my favorite book because that one's old right now. PHP Master is pretty awesome. Plus, I've already been paid for it, so that's not like I'm not getting paid for that plug. I'm a contributor to Zen Framework 1 and 2, PHP Docs, PHP Internals. I'm the original creator of FAR and PHP Archives. So what that means is I wrote the PHP version and someone way smarter wrote the C version that ended up in PHP 5.3. I am the lead for PHP Women in the US, which is why I have this little guy up here. Towards the end of the year, you'll be able to buy those from us, $25 a piece. Support our cause. And I'm at dshafik on Twitter. You should know before I start that I am hard of hearing. Everyone forgets this, and it's actually a little worse today because I'm a little congested, so I will have to come out and get questions. Before I start, I want to let you guys know how I run my slides. Basically, I have a title slide that looks like this, and this is what I'll be talking to, because there's two things I hate with other speakers is a bunch of bullet points that end up being subtitles, and I can read faster than they can talk. And then I hear about a great talk, and I go online, and it's 18 pictures of cats with random words, right? So behind it, I'll have decent bullet points that you all can look up later. So I wanted to talk about how I got to writing this talk and how I started researching the stuff that went into this talk. It basically all started with profiling. I spent a lot of time working with xhprof and xdebug profiler. I have 3 blog posts waiting to go up about that stuff. And I was profiling WordPress. I figured if I can get even a 1% performance gain over 18 to 22% of the internet, that's kind of a reasonable win. I ended up with 18% if both patches get in, so that's kind of cool, right? But I kind of want to mention a little bit about benchmarking versus profiling. So profiling records the relative speed of the function calls in your application. What that means is that the act of profiling actively destroys the timing. So it's all about relative timing. It's kind of like quantum physics. Observing it kind of breaks it, right? Whereas benchmarking tests actual speed. So if you want to know the actual performance of your app, profiling is not the way to go. So I use what's called the performance loop, which looks a little bit like this. So basically, I benchmark to see current performance. That's what my users are actually seeing. I profile to figure out what my bottlenecks might be. I make changes. And then I benchmark again to see what the actual changes are. I've actually seen it where with profiling it looks faster, with benchmarking it looks slower. So a very common question that you should answer is, when should I be profiling my code? First question you need to ask is, do I have a problem? I think the most common problem I see with performance tuning is assuming that you even have a problem, and perimeter optimization is a waste of time. So the way I go about this is I determine if I have a problem, I benchmark. But to do a benchmark and figure out if you have a problem, you have to decide what your results, what you want them to be. So I want 100 concurrent users with sub 10 millisecond response times, right? If you don't have something to benchmark against, some goal to reach, you don't even know if you have a problem or how big it is. So there are a bunch of common causes of slowdowns. The most common one is your data store. It doesn't matter if you're using Mongo or MySQL or whatever. That's going to be your most common cause of slowdown. External resources, APIs, file systems, network sockets, all those kind of things. And then the least common is bad code. And I like to say that the only great code is code that never has to run. Everything else is just good code at best. And if it's code that never has to run, you probably should be removing it, right? But really what I mean is code that you can cache and not run frequently is the best kind of code. So basically, if you're at the point where code is your bottleneck, you're kind of in trouble and there's no magic bullet. So that's how I got to this talk. Actually looking at the performance of code and why it is doing what it is doing. So we're going to start off with internals 101, looking at the execution lifecycle. I really hope these animations work a little bit. So this is what the execution lifecycle of PHP looks like. Most people will say that PHP is not compiled, but that's not entirely true. PHP is compiled, it just happens every single time. So basically, we take our PHP script, we execute it with the PHP binary. It is parsed into a list of tokens, which are then compiled into opcodes, which are very similar to Java bytecodes, and then they're executed on the Zend engine, which is a virtual machine. And then we have output. So this middle part is actually the PHP interpreter. That's the PHP binary. Now, I already mentioned Java, and the reason I did that is because it is actually very similar to PHP. Now, Java obviously is a compiled language, but if we look at this, it's a very similar process, except that the parsing and the compilation to bytecodes in this case, we save that result, and then we can just rerun that part. Because when we reparse it, we're not going to get a different result. We're not going to get a different set of opcodes or bytecodes out of it. So we do this in PHP also, maybe, by bringing in an opcode cache. So up until now, with PHP before 5.5, we would have probably used APC. With 5.5 plus, we're looking at Zend opcache. They both work essentially the same way, which is that they take the result of the parsing and compilation to opcode step, and they store it not in a binary file, but in memory. And then we can just reuse that step. And that is why we get a huge performance increase with an opcode cache, because the parsing and the compilation is actually really quite slow. So as we look at this, we run the PHP script. We add an extra step where we check the opcode cache. Is it already done? Yes?
Doesn't PHP still check to see whether the file has changed?
Well, that's exactly what this opcode cache check does. So it checks if the file has changed, rather, if what's in the opcode cache matches what's on disk. So we check the opcode cache to make sure that it's up to date. If it's not, we parse it, compile it, and we save it, and then we execute it. Yes?
I was just going to add, so you mentioned the op cache, the in 5.5.
Yes.
Now, didn't they change the way that detects whether the file has changed or not?
So there's
it's using paths instead of inodes.
Yeah. So the way that it checks for stuff on disk is different, but the process in terms of like this diagram does not change. If it has already been cached, we just read it from the shared memory, we execute it. Either path we go through, we go to the Zend engine VM and straight to output. So it is similar or more similar to Java or another compiled language than to traditional PHP or interpreted languages. So back to this. We're not going to look at op caches anymore because we're not really focused on that. What we're going to focus on is these three steps, so what's actually happening inside the interpreter. So the first step is tokenizing. This is the parsing step. So I want to introduce you to the worst hello world ever. If you could over-engineer a hello world, this is what it would look like. It always pains me to do this slide, but it's a great example to work with because everybody gets the code immediately, right? So we have a class called greeting with a function say hello. One argument, $2, we echo hello $2. We instantiate it and pass in world, right? What this looks like when we tokenize it is this. So it's two, like that's the first bit, that's the second bit. So if you look here, tokens are basically represented by a constant, which starts with T underscore. Everything in PHP can be represented by a token, except that stuff that is a single character, or less, but that is a single character. So basically tokens are integers, and if it can be represented by a single character, that takes up just as much memory as the integer. There's no point in using anything else. So rather than have a token and a value, like in the case of the open tag, we just have the tokens itself. So if you look there, for example, and here, so it's basically curly braces, parentheses, square brackets, quotes. All those will not have a T underscore type deal. So if we look through this, we can actually see all the code here is represented. So we have our open tag from our PHP file, our class. We have a little bit of white space, so all white space is represented. Where's my, there it is. Greeting, open up the class, public, function, say hello. Everyone's getting this? Yes?
What's the point of the white space giving tokens when white space is essentially ignored anyway?
That's how we know to ignore it. So at this point, we're just trying to figure out what everything is so that we can then turn it into opcodes. So we're not executing anything at this point. We're just identifying every part of the script so that we can then correctly turn it into the underlying executed opcodes. And so obviously you can't see the white space here, but any contiguous amount of white space goes into one token, which can then be ignored or discarded. Now, white space does actually have some effect. If you think about the way the ternary operator changed, question mark colon with no space now is different to question mark space and then two conditions on either side of the colon, right? So white space can have some effect. Let me see if there's anything else interesting here. So, for example, here we have T escaped and white space. So basically we have some text that has got escape or could have escape codes in it. You'll notice that the variable is a separate token. So we break out the quotes, the variables, and the static strings all within. This is where interpolation starts to happen. I want to highlight that a little bit more. The difference between interpolated and non-interpolated strings. So this is actually really interesting. Within our script, I'll pull that right back up here, we have two strings here. We have hello $2, which is obviously a double-quoted string with an interpolated variable, and we have a straight world, but it's also double-quoted, and that's really important to note. When we get to the token stage, the one with a variable in it that has an interpolated variable is 4 different tokens. The 2 quotes, the T escaped, and white space, and T variable. And the non-interpolated one, even though it is still a double-quoted string, is a single token. So this T constant escaped will be used for single-quoted and double-quoted without interpolated variable strings. So when you hear single quotes is faster than double quotes, that's not necessarily true if you're not actually interpolating. So you can see why this stuff starts to matter in terms of performance, why... Like obviously generating 4 tokens and handling 4 tokens is going to be slower than handling 1, but don't get caught up in the micro-optimizations. There really isn't an optimization to be made here. If you were to concatenate, it would be even worse. So there are 4 different ways that I can think of reasonably to define a string. Double quotes without interpolation, single quotes without interpolation, you can see they're identical. Interpolated or simple interpolation, so $A bar, we've got that 4 tokens that we had on the previous screen. And then this one right here. This is what you'll typically use when you're using arrays or something inside of a string and you don't want to concatenate. This is the only thing that does not follow the rule of single character does not have a token. This T curly open in this one instance, and it's actually a bug. Well, it's not. It was brought in for the PHP 6 Unicode stuff and never thrown out. So it just doesn't matter. But yeah, so we can see that this one turns into 1, 2, 3, 4, 5, 6, 7 tokens, right? We'll get back to this example just a little bit later when we actually look at opcodes, which we're going to get to now. Any questions on tokens before I move on? Okay.
Would we ever need to see the tokens for our PHP code? Does it ever get to the point where that's an optimization that we should be making?
It's not an optimization that you may want to use, but you can do like static analysis stuff by programmatically looking at the tokens. I don't think you'd want to see them by eye necessarily. And actually, when I wrote this stuff, I was dumping I had a script that would dump the tokens. That was how I'd get them out. And I wrote tokenize the code, the file, and it outputted tokens nicely in a formatted table. I went, what the heck happened? That's not what my script does. Apparently, past me had written a script to dump stuff nicely so I could read it, and treated me as an idiot because he did it again. Sorry, you had a question as well?
You said concatenation was worse. Is it just tokenize it more?
I'll show you some concatenation later in the opcodes. It's only worse. It depends what you're doing. Concatenation also brings a whole lot more features to it. You can obviously add like functions and stuff in there and all sorts of stuff. So concatenation is kind of a different ball game to just having straight strings. One of you, yes, you.
I had the same.
Oh, you had the same question?
If hello world were concatenated,
Yeah.
how would that look?
Okay, yeah, we will see that in tokens later. It doesn't really matter at the tokenization stage. Sorry, in opcodes later. It doesn't really matter at the tokenization stage. So opcodes. So this is the second part of our process of getting our code ready to run. We take our parsed tokens and we turn it into opcodes. And I do have a story about this, which is that at Lone Star PHP in Dallas 2 years ago, I gave a talk on profiling, and I ended it with a section on APC and how that works kind of under the hood. And I mentioned tokens as opcodes. I didn't get them confused, and I knew there was a difference, but I didn't really know what that difference was. And Derek Bertans, who works with Jeremy over here at Mongo, he said, you know, those really aren't opcodes. And I said, I know, but like tokens are a way to get it across. Like people get that because it represents the code kind of one-to-one. So I went away and I did, all this kind of research. And just recently, Derek came onto the PHP Peckle channel, and he went, hey, Davey, what's this thing in Zend-Opcast? Like, what does it do? And I'm like, I know the answer to this. I started answering. He goes, oh, wait, I mean Dimitri, who works for Zend. I'm like, I actually still know the answer to this. So then I actually got to school Derek about opcodes. So I'm like, yes, full circle. So opcodes. Speaking of Derek, VLD, Vulkan Logic Dumper. Nice segue, right? So this was used to be called the Vulkan Logic Disassembler, but now is the Vulkan Logic Dumper. It is not the only way to get the opcodes out. There are newer ways, but this way works really nicely for me. It's installed via Peckle. So Peckle install VLD beta, because everything in Peckle is beta. We add the extension to PHP INI. It's just a straight extension, not a Zend extension. And then we basically, on the command line, we do PHP, and then we specify 2 INI flags so that it's not running with every script. We just do it on the script that we're asking for. So these 2 flags are to activate VLD, and then this one actually turns off the execution of the code. We just get the dump of the opcodes. And obviously, we specify the file. So VLD outputs 3 different parts. The global code, so anything that's part of what's called your main script, global functions, and then class functions. Looking at those dumps, they all start with a header. So in this case, we've got a class called greeting. We're in the function say hello in our file greeting.php, and for some reason it says the function name again. I haven't figured out why. We then have the number of ops, which is the total number of opcodes that get dumped. And then we have this line, and this line is super important. So this talks about compiled variables, and we'll get to those a little bit later. But basically, this tells you the relationship between userland variables and compiled opcode variables. The last part of the dump is the actual opcodes. So it's basically a table, and there are multiple columns on this table. The line is the line number in the source code, and I know I said I wouldn't have subtitles, but you kind of have to. The opcode number, so basically 1 through whatever. Entry, so what this is, entry and exit points. Basically, when you enter into a function or you exit out of a function, there's a little greater than symbol, and in that column of 3 characters, it's left aligned or right aligned. It's really hard to see, but it is actually really interesting to look at. The opcode name, details on global variable fetches. This one took me forever to figure out, and in fact, Derek didn't even know what that column was for anymore. But basically, anytime that you use the global keyword or access a $_ super global, then there'll be something in that column. The ext column, so this is going to differ per opcode. What's in there is basically an extra space to store information. So in the case of a jump opcode, it will tell you where to jump to, which opcode to jump to. The return, so whenever the opcode is executed, this is the return where it's going to store it. And then finally, the operand. So if it is a concatenation or a plus, it'll be the variables that go on either side of that operator. So as I mentioned, variables, compile variables specifically, there are 4 types of variables in PHP internally. There are exclamation point variables, which are compiled variables. These are directly related to the variables that you have in your PHP code. Then you have tilde variables. These are temporary variables. So anytime that you do something that needs memory storage under the hood. For example, if you pass in a non-variable to something that expects something that's referenced, it will create a temporary variable. And then not know what to do with it, but that's what it'll do. We'll see those a lot later. Dollar variables, they're another type of temporary variable. The only difference is that they are similar to userland variables, so compiled variables, in that they need things like ref counting. So they're kind of used pretty much only in one spot that I've seen, which is when you instantiate an object, it needs to store it temporarily somewhere, but it needs to know how many things are pointing to it. So it needs ref counting. It's not just as dumb as a temporary variable. And then finally, colon prefixed variables. These are also temporary, and the only thing they're used for is when we look up a class in the hash table, it will contain the location of that class so that we can instantiate it. All of these are numeric. So the one thing you can't do in PHP is have a variable that starts with a number. And all of them are only numeric. So go figure. So back to our code and dumping it. So this is our class. if we go ahead and dump the opcodes for this, so this is actually the call to say hello. What ends up happening is we're in class greeting, function say hello. We have 5 opcodes. That's all that this class outputs. We have one compile variable, which is, I always call them not, but exclamation point 0, which is our $2 variable, which is our argument into say hello. We then have our actual output. So the first thing that we see is we have a receive. So inside of any function where a parameter is passed in, the receive opcode is what handles bringing in that data and bringing it inside the scope of the function. Then we have an add string. So we create a temporary variable, $0, and we assign hello to it. So the first part of our string. Now, if you remember, this echo hello2 was 4 opcodes, the double quotes, the hello, and the $2, right? So the first thing we do is create a temporary variable, and we add hello to it. You'll notice spaces are indicated by pluses. After this, we then concatenate our contents of our variable, $2, to the temporary variable. So this is a concatenation because it's an interpolation. So when I say concat, that's what's happening on the C level. It's in concatenation at the C level. But at the PHP opcode level, it's called add var. So what this does is it adds the value of one variable onto another one. In this case, we're adding the value of a compiled variable, exclamation point 0, to a temporary variable, $0. And then we echo out the temporary variable. So when we do this string here, this interpolation, it results in a temporary variable that the echo can then display. If we were to echo out a actual variable, so if we just did echo $2, it would be echo, and then this would be exclamation point 0 instead of $0. And then we have this return null. Because we have no explicit return, there's an implicit return of null. So if you've ever done PHP docs and you do @return void, this is what's actually happening under the engine. Now we get to the main script. Now, as I said, VLD will actually dump this bit first, but I felt it was easier to start with the function because this interacts with that. So there's only 2 lines of code here, but we get almost double the opcodes. So we start with a NOP that we can ignore, so a no-op. I'm not actually sure why it's there. I'd also like to point out there's no code that syntax highlights these. I do it by hand in Keynote. So the first thing we do is we do a fetch class. So as I mentioned earlier, we have these colon prefixed variables, which are the result of a lookup. So we're going to look up the greeting class in the hash table. We store that in :1. I have no idea what the extra is here. Nobody cares. We then do a new opcode. So this is actually what instantiates a instance of our class. So we're going to instantiate an instance of the greeting class, :1, and store it in a ref-counted temporary variable $2. Then we have do fcall by name. What this does is this starts, that's actually calling the constructor. So in this case, it's automatically calling the constructor. It's very interesting to note that these things happen separately. If anyone has used PDO and you've done fetch class or fetch object and told it the type of object you want it to use, you may have noticed that it assigns the properties to that object prior to actually calling the code in the constructor. And this is how it does it. Between those 2 opcodes, that's where the assignment would happen, and then it would call the constructor right here. The next thing we do is we assign the instance to our first compiled variable. So that's basically all we've done here is new greeting. So this is the greeting. This is the new. We've called the constructor, and then we've assigned it. So that's the equal sign up there, and we're assigning it to $greeter, which is exclamation point 0. Then we do an init method call. So you're going to see this quite a bit when we come to any kind of function call that's not a constructor. Function calls are done in a multi-step process. So first we init it. We say that we're going to be calling on the object stored in exclamation point 0. We're going to call the say hello method. Then we're going to send in a value. So this is our argument. So if you remember on the previous slide here, we have a receive. Send val is how we pass in arguments. So for every argument that you have going in, you'll have a send val. And then we do fcall by name again. So that actually calls the function. And then we have a return of 1. The main scope will always return 1, unless you do like a die 0 or something, I guess. But return 1 is implicit. Any questions so far? So variables. We've talked about internal variables, but I want to talk about userland variables now. PHP without variables is a really, really bad language, right? So they are, I would say, next to arrays, they're the most important part of the language that we have. And all variables are represented under the hood by what's called a zval, or a Zen value. They are a C data structure. They're used to store all userland data. And they're probably the most important thing in PHP. So what these look like, they are a struct. Yes, sorry, just scratching his head. They're a struct with 4 different properties in it. The first one, value, stores the actual data. We have ref count GC, which is the number of references to the zval. Now, it's really important to understand that references on zvals may or may not be related to references in userland. Then we have the type, which is the type of data. Is it a string? Is it an integer? And then this last one is whether or not it is actually a userland reference, so whether we've got that ampersand. So the data itself, so that first property value, stores a union, a C union. Is anyone familiar with C unions? So basically what they are is they're a data structure that have the potential to store multiple pieces of data, but they can only actually store one. The memory that is assigned to them is as large as the largest member, and that can be kind of important later because things do change because of it. So it's important to understand that they're strongly typed because it's C, right? So we have longs, which are straight integers, doubles, which are floats. Then we have this struct, which is for strings. So strings are stored as 2 parts. The actual string value is characters, and then the length of the string. So when you call strlen, it doesn't literally calculate the length of the string. It just checks the underlying zval value for the length. Then we have hash tables, which is for arrays, and then send object value, which is a pointer over to objects. So this is what is stored in the value property. So as I mentioned, they are strongly typed. Yes?
So that means every time you change a string, it's going to count the length.
Every time you change, yes. So every time you change a string, it will recalculate, or not recalculate the length, but it'll figure out the length and store it. I guess a lot of C operations will kind of return string values, length values and stuff. So PHP is, well, everyone says it's loosely typed or not typed, but under the hood it is strongly typed, and it's important to understand that. So at the C level, everything is strongly typed. What that means is that PHP coerces the data automatically for things like comparisons. So that's why 0 == false, because it'll turn one side into the other type and then do the comparison. Triple equals will just stop the coercion. It's also important to understand that PHP will never change the type of the underlying zval. Once it has been created, its type never changes. So even if you cast, say, an object to an array and store it in the same value, it doesn't just change that zval. It creates another value and assigns it. So there are 8 different types of values. Nulls, I'll just throw this up. Nulls, integers, floats, strings, arrays, objects, booleans, and resources. I've misspelled resource. What's really interesting here is where they're stored. So there is no storage for a null because they're an absence of a value. Integers are stored in lval as a long. Floats are stored in dval as a double. Strings, as I mentioned, they're stored in 2 parts, value and length. The arrays are stored in the hash table, objects in the object. Now these 2, however, are interesting. The booleans and the resources are stored in lval. And the reason for that is that under the hood, they are integers. So we could define both a boolean and some other property on that union, but there's no point. We have no memory savings. If you store the one inside of the long here, or you store it in a boolean, it's not going to make any difference. So they just reuse the same place. And because there's an identifier telling you what type of variable is stored inside this union, it doesn't matter. Any questions before I move on to this, because this gets a little complicated?
Where does it store the thing that shows what type it is? Outside the union, right?
Here. So this type property. In the zval struct, the type is one of, is it going to go? So the type is set to one of these.
Char, byte, calculated, got it.
And if you ever look at the C code for this stuff, There are fetches to grab the values that are specific to the type. So you check the type and then perform the correct fetch to get the correct data. So references and copy on write. So I mentioned that under the hood, there's something called ref counting, which is references, and then there are PHP references, and they are one and the same, but also different. So one of the really cool optimizations that PHP has under the hood is to avoid copying values and duplicating memory. It utilizes something called reference counting and does something called copy on write. So basically what that means is when you assign one variable to another without an ampersand, you're not doing a reference, it actually still under the hood is a reference. And it will remain a reference until either side of that variable is changed. So it'll just keep pointing to the same memory location. So it is different from using the ampersands, but under the hood it's using that reference counting stuff that the PHP references use to ensure that memory is not duplicated unnecessarily. It is easier to show this with examples, I think. So $a equals 1. We create a single Zen value, a z-val, number 1, with a value of 1 and a ref count of 1. Then we assign $b to $a. So this is not a reference assignment, but what we do is we increment ref count to 2. And we say that this particular variable, this memory space, this z-val has 2 variables that point to it. Because we're not saying that it's a reference, it understands that if one modifies, we need to fix it. We do c equals b, so even though it's not pointing to the original a, we still just bump the ref count. When we then increment a, rather than create 3 separate z-vals, we take the first z-val and we leave it alone except we decrement the ref count. So we're disassociating $a with that z-val that it first created. And then we create a second one and give it the new value with a ref count of 1. If we unset b, z-val just gets its ref count decremented by 1. And then if we unset c, z-val number 1 is destroyed and a is still pointing to z-val number 2. Anyone not getting this? Oops, that was important. Sorry. So when we then look at references, it's very similar. The main difference is that we now say is ref equals 1 when we use that equals ampersand. If we then increment b, rather than creating a new z-val and assigning like we did before, we just increment the value because everything is pointing to the same thing as a reference. So a slightly more complicated example, a equals 1, b equals a, c equals b. So this is the very first example that we started with. Then we do a reference between d and c. Okay, so right now, a, b, and c are pointing to the same z-val, number 1, with a ref count of 3 and isRef equals 0, so we don't have a PHP reference. Then we do this assignment. And again, PHP is very smart. Rather than create 2 new z-vals or split it up really weirdly, what it does is it leaves the first one alone. It says this one is not referenced. Leave this one alone, leave everything that's pointing to it that's not changing, pointing to that one, and then create a second z-val and change where the 2 sides of that reference are pointing to. So we haven't changed the value. All we've done is created a second z-val that is now referenced rather than the first one that was not. So what that means now is that if we modify either side of that reference, D or C, it will not modify z-val number 1. It will only modify z-val number 2. All good? Any questions? Okay. So we're going to look at more opcodes. Basically looking through some common things that we'll do and what those look like under the hood. So incrementing by 1, more than one way to do it. I can think of, I believe, 4 I came up with. I'm sure there's way more than that, but those are the simple ones. So post increment, we use this a lot probably in for loops. Everyone uses post increment. So what this looks like under the hood, we assign 1 to our compiled variable $i. We then do the post increment opcode. So to do this, what we do is we increment the value and store it in this tilde1, and then we free the value. So in this case, because we're not doing anything with the value, we just store it somewhere and then we ditch it. When we're doing a for loop, we're actually doing a very similar thing. We're actually creating a temporary value that we don't need. There's an assignment back to !0, which is our $I that we need, but we don't need the temporary return that happens. So one of the premature optimizations or micro optimizations that people say is to switch to pre-increment. And the reason that this is better is rather than storing in a temporary variable, because nothing is returned, we can just do a straight up increment and see on the compiled variable. So it's one opcode less and uses one less piece of memory. So reassignment, this is probably the most inefficient way to increment by one. So $I equals 1, $I equals $I plus 1. So we're reassigning back over the variable that happens. And this is why in PHP you can actually do that and it won't mess up by reassigning back to itself even though it's used in the operation, is because of the way this works. So we do our assignment of 1 to our compiled variable. We add 1 to that compiled variable. We store it in a temporary location. This temporary variable is why reassignment works correctly. And then we assign the temporary variable back to our compiled variable. And then assign add, this is my preference because you can also increment by 2 or 3 or 4, right? So the plus equals operator, it's also a single operation like pre-increment. So we assign to our compiler variable, we do our assignment addition, so whatever's in our compiler variable, we add whatever's on the right-hand side there, in this case 1, and then we have an implicit return of 1 again. So that's assign add. So I mentioned we get back to quoting strings. So under the hood, single quotes look like this. So basically echo and then the operand of bar. There's nothing hugely crazy there, but it actually mirrors our tokens. Double quotes, exactly the same. What's interesting here is this is still using single quotes because PHP just doesn't care at this point. Then we get on to the simple interpolation, so this $A bar inside the string without our curly parentheses. We have an assignment to our temporary variable of foo. We then do this add variable, which is the kind of under the hood concatenation. We store it in a temporary, we actually create a temporary variable just to store the value of our compiled variable. We do the add string, which is an actual concatenation. And then we echo out the temporary variable. What's really interesting is this complex interpolation that was like twice as many tokens is identical once we get to this point. So this right here is identical to this right here. So what that means is if you have an op cache, even though there's a whole bunch more tokens generated by this piece of code with an op cache, there's absolutely no difference in performance. And also because we're using compiled variables, it doesn't matter that it's a simple variable like $A or if it's something like an array. So concatenation, any questions on the string stuff? Okay, so concatenation. $A equals foo, $A equals $A dot bar. We have an assignment where we assign the simple value of foo to our compiled variable !0. We have our concat operator, which takes the compiled variable and the string to concat, again, plus to represent spaces. We assign that to a temporary variable, and then we assign that temporary variable back to our compiled variable because we have a reassignment. If you have like multiple concats and function calls in there, that temporary variable allows us to work on that and potentially reuse $A later on in that expression on the right-hand side of the equals before it's modified. So if this reassigns straight back to !0, anything that followed, say for example we had $A dot bar dot $A again, so you wanted to repeat $A, if this reassigned back to the compiled variable, that second concatenation would reuse the string that has now got the extra bar in it, right? So by putting in a temporary variable, we can complete the right-hand side of the expression independent of, or reusing the original value of the variable that's being modified. So assign concat, just like assign equals, or assign plus, this is the most efficient way to concatenate, at least simple values like this. So we assign foo to our compiled variable. Because we're doing assign concat, we do it all in one operator. It goes straight back into our compiled variable. If you were to do more on there, like an extra concat, like a regular concat, that's when we start to bring in temporary variables, but a simple assign concat like this will not use a temporary variable. So any questions on concatenation? Did that answer your questions on concatenation earlier? Okay, that's good. So function and method calls, I believe this is the last part, and we're getting a little late on time, so that's great. So a very simple function call, PHP info, it's just a straight do f call. There's no arguments because we haven't specified any, but we could. So it's just a straight do f call, that's it. However, once we start to add in arguments, we now start to see these send vals. So send val 1, send val 3, those are the two arguments that are going into our BC add. Then we do the function call. If we were to re-implement BC add in userland, obviously it doesn't support like super large numbers or anything, but very simply add two arguments, c equals a plus b, return c, and then we call it with the same arguments. It looks fairly similar. So we send val 1 and 3, call our add function. There's not much different going on there, but we also now can see the calling side of that. So we have multiple variables that are being passed or that are being received. So these are the arguments a and b. So exclamation point 0, exclamation point 1. So there's one received for every send var. We then do our addition and put it in a temporary variable. Temporary variable is then assigned to our last compile variable $2. Exclamation point 2. And then we return that. So that's what the other side of BC add would look like if it was implemented in userland. Method overloading. So if you have a class that has double underscore call and you call a function that doesn't exist, most people assume that this is a lot slower because like there's magic happening. But it's actually really interesting what happens here. So we do a class lookup of foo. We assign it to :1. We instantiate that because we do that separately from our constructor. So we instantiate it and assign it to $2. And then we call the constructor with the doF call by name. It's opcode 3. We then assign that to our compiled variable. So I don't know if you can see, this is the code that we're actually running right here. So we assign it back to $foo. Then we start our method call to bar. And if you remember earlier, we init the method call, then we have an option to send in parameters, and then we actually call it. Because we have no parameters, it's basically init followed immediately by the call. Then we do the same thing for bat, which doesn't exist. So that's actually going to go through double underscore call, which is our magic method, and it's exactly the same. So what's important to note here is opcodes are not infallible. They are not a direct, necessarily a direct explanation of what's happening under the hood. doF call by name maps to a C function, which itself will then say, hey, does this exist? No, it doesn't. Does double underscore call exist? Yes, it does, and make that determination and call it. Okay? So it is slower, but it doesn't look slower from the opcodes. Okay? So that's important to understand. So that's it. If there's any questions, I'd love to hear them. Before I just come and get that, feedback on joined in, I really do appreciate it. I'm giving this talk again in about a week, so anything I can do to improve it would be fantastic, or hit me up on Twitter. Slides will be available, and that's it. So you had a question, yes?
Yeah, so what micro-optimizations would you say are the most significant to pay attention to?
So what I will say about all the micro-optimizations that I can come up with for that answer is the Zend op cache pretty much does them automatically. So turning post-increment into pre-increment, it'll check to see if it's being assigned to a variable. If it's not, it will turn it into a pre-increment automatically. Zend op cache is the best optimization that you can put in place for this. The use for this is to actually make sure your code is doing something that it shouldn't, or is not doing something you don't think it is doing. It's primarily, I would say, a debugging tool at this point, but I just find it really interesting to know. Yes. Sorry.
So I'm still stuck on 5.2.
Yes, I'm sorry.
Unfortunately.
You should have come to my talk yesterday.
Oh, I did actually.
Oh, okay.
So is the Zend op cache like built into 5.5?
It is distributed with 5.5 and can be enabled automatically, but it is available for 5.2 plus.
Okay.
So you can go grab it. APC otherwise.
Yeah, I am using APC.
Yeah, APC will give you. It doesn't have. It basically doesn't do any of the optimizations.
This is actually part of my
Okay.
question. So isn't it everywhere?
Isn't
The
what up?
Zend optimizations, aren't they everywhere now?
They could potentially be available. Yeah, if you turn on Zend op cache, then yes.
After 5.3.
No, it's after 5.5.
Or 5.5?
Yeah, you can download it for 5.2 plus, but it's distributed with PHP 5.5 plus. Any other questions? Not from that side of the room. All right, thank you, everyone.